Yeah. So first of all, this device that I'm writing on allows me to write in terrible handwriting. So yeah, you have to bear with that. Cool.
Yeah, we are used to it.
Yeah. So I'll start by talking about orders on sets. Orders on sets. I'll be assuming that you know what a set is, because why not? And I'll be defining what a pre-order is. A set X with a binary relation less than is called a pre-order. Yes. The following holds. First, for every element in the set, you should have A less than equal to A. And for every A, B, and C in the set, you should have whenever A less than equal to B and B less than equal to C, you should have A less than equal to C. And it works nicely that whenever these conditions are satisfied, we call the set a pre-order under this relation. For example, let's say you have X, which is just 3 elements, U, V, W, and suppose the relations are the relation is given as follows. Yeah, so what I'm saying is every yeah, so wherever there is a directed arrow, think of that as the relation less than equal. So what this pre-order is U less than equal to U, V less than equal to V, W less than equal to W, and we also have U less than equal to V, V less than equal to W, W less than equal to U. And you can easily check that both the conditions are satisfied and this set is a pre-order. Cool. But
we say that a set is pre-order or a set with this relation is a pre-order. What's
yes,
the correct?
the standard notation is the pair X comma the relation is a pre-order.
All right.
Wait, we have U less than equal to V and V less than equal to W. Wouldn't we need U less than equal to W?
Yes. See, so what happens in a pre-order is this type of ugliness, as I like to call it, happens. You can have two elements which are both less than equal to the other, but they are not equal.
Okay.
Because you see, we are not imposing that condition yet. But good thing you mentioned that. Let's define what is let's define what we call a partial order. A set X with a binary operation. The binary relation.
Yeah, the above one is not a pre-order, right?
It is.
Like U less than V, V less than W. U is not less than W.
Yes. Let's
Both side arrows should be there, I guess, right?
Yeah. Let's take care of that. Everything is less than equal to everything.
Yeah.
Cool.
Yeah.
Now I want to take care of what someone just asked, what if we have two elements which are both less than equal to each other, but they're not equal? So that is taken care of in a partial order. So a partial order is just a pre-order with a restriction. So we say that x with less than is a partial order if it is first of all a pre-order, and secondly, for all a comma b, a less than equal to b and b less than equal to a together gives you a equals b. Now you see this thing is taken care of. In a partial order, the ugliness that we saw earlier would never happen. Yeah, cool. But even in a partial order, you do realize that not every pair of elements have to be related by the relation. For example, let's look at this set. Let's say we have this, this, so we have this, let's say we have this. We have 4 elements, and you see that these 2 elements are not related at all. You can't compare them, which is fine in a partial order, but it's not fine in what we call a total order. A set X with binary relation less than equal to is a total order, or you also call it a chain if, again, the following. First of all, it's a partial order. And secondly, for all A and B in the set, either A less than equal to B or B less than equal to A. One of these holds, at least one of these holds, meaning any 2 elements are comparable. Then we would call it a total order or a chain. And you realize that if we were to add an arrow over here, this would make this a chain. Of course, I'm not writing the loops. The loops are always there.
What do you mean by like a less than equal to b and v b less than equal to a?
Oh, that's OR, the logical OR.
Oh,
Hold on, I'll write it in English. Okay. It's just saying that any 2 elements are comparable. Cool so far? So what we did is we defined a pre-order where you have symmetry and transitivity, meaning A less than equal to A for every A, and A less than B, B less than C gives you A less than C. But we wouldn't want to have elements which are less than each other, pairs of elements which are not equal. For that, we add another condition, which is this. Whenever A is less than equal to B and B is less than equal to A, we have A equals B. That gives you a partial order. But still, the problem is not every pair of elements is comparable. So we define what a total order is by putting the last constraint, that is, any 2 elements are comparable. Cool. So now we know what the partial order is, and now we know what the total order is. Now I want to define something. Definition. Let x comma less than equal to, let this be a partial order. Oh, by the way, partially ordered sets are also called cosets very lovingly. We call them posets, and totally ordered sets are called tosets.
First time I've heard a funny name. That's-
Yeah, it's a very loving and endearing name given to partially ordered sets by set theorists. We call them posets for fun. So let x comma less than equal to be a poset.
Is
And
this in honor of Ocean law?
no, it's just PO stands for partially ordered.
Yeah, I see.
Yeah, let u be let u be a subset of x. We say that an element u belonging to x is an upper bound of u if u of y. If v less than equal to u for all v, right? Meaning, first of all, u is comparable with every element of capital U, and not just comparable, it's greater than or equal to every element. It's bigger than every.
Also, U not necessarily belongs to U, capital U, right?
Yes. U need not belong to U. U just has to be an element in the quotient. Then it's an upper bound.
It can be in U also, like the maximal element in U.
Sorry?
It can be the maximal element in U also.
Yes, it can. If it's the maximal element of, if it's a maximal element of U and it's an upper bound of U, it will turn out to be the greatest element of U. But yeah, we'll get to that. An element. Let's call it something. Let's call it W. W belonging to
Also,
U.
I have
This
one doubt.
Yeah.
Let's say we have like two elements, U and V. Suppose U is comparable with every element of X and it's the upper bound of X.
okay.
And we know that U is less than equal to V.
Hmm.
Then can we say V is also an upper bound of X?
You see, we are working in a poset, and U is greater than every element of the set.
Yeah. Oh, and
And
so we should also be comparable, right? Yeah.
exactly, but then U and V will become equal, right? Because it's a poset. U less
Right.
than equal to V, V less than equal to U.
Oh, I didn't say V less than equal to U. How did V less than
But I guess they are not
You said
comparable.
U is an
since
upper
it-
bound of U or X. You said X.
No, U is an upper bound of capital U, I meant basically.
I see.
Yeah.
Oh yeah,
but
then
since
yeah, if U is an upper bound of U, then everything greater than U also becomes an upper bound.
Okay. And it has to be comparable by a definition of poset, right?
Yes, by transitivity.
means
Also-
like each element of X is comparable with U.
Each element of capital U is comparable with U.
Yes, yes, yes.
Also, a partial order set is poset or pre-order?
Oh, partial order. Partial
Oh,
order.
okay.
Pre-orders are in general not very beautiful objects. We don't
Right. Okay.
work with them that often in set theory. Although they do show up in category theory. Anyway, let's not go there. I romanticize category theory. Anyway, yeah. So an element of the set X is an upper bound of U if that element is comparable with every element of U and is greater than equal to every element. Now, yeah. An element belonging to U. Okay, the same setup. Let X comma less than equal to be a partially ordered set. Let capital U be a subset of X. Then an element W of the set U is called a maximal element of U if for all X belonging to U, variable notation should not be using X. For all A belonging to U, we have A less than equal to W, or W not less than equal to 0. Does that make sense?
What does W not less than equal to A mean?
It just
They are
means
not comparable.
they are not comparable, or if they are comparable, W is not less than equal to A.
How does that work?
Less than equal to is a relation, right?
We are defining it like they we can't relate them. But because
Yeah.
since in partial order it's set, we don't have that each element is comparable.
It's a relation, meaning it's a subset of X cross X. So all we are saying is the pair W comma A does not belong to that relation. Okay, let me give you an example. Let's say you have this partial order, the same one that we started with last time. Yeah, and loops at every point. Now let's say this is my W. Can you see that it satisfies all the conditions of a maximal element? For example, yeah, this is X and U is also X in this example. So U is a maximal element of X in this. What am I saying? W is a maximal element of X in this.
The thing is that like we can have more than one maximal element in
Yes.
a partially ordered set, right?
Yes, you have this element W prime, which is also a maximal element, as you can see. So an upper bound, the important distinction here is an upper bound is an element which is greater than everything in U. Whereas
Means it
a
is
maximal
comparable.
element, yes, it is comparable and it is greater than everything in the set U. Whereas a maximal element is something such that there is nothing greater than that in the set. Does that make sense? For example, you look at this W prime over here. This guy, pretty little guy here. It's not less than W, but it doesn't matter because it's not greater than W. You see, there is no arrow going from W to W prime. That's all that matters. Get it? There is nothing strictly greater than W.
Right. So basically, W not less than equal to A means they are just not comparable, right?
Yeah, they're not comparable, or A is less than equal to W.
All right.
Make sense?
Yeah.
Okay, cool. So in this example, W and W prime are both maximal elements of the set X. Also, one more definition, let X comma less than equal to be partially ordered set, therefore set. Let B be a subset of X. Then an element B of capital B is called the least element, least or smallest or first element, whatever you want to call it. Of B if for all A belonging to B, B is less than equal to A. So if you go to the same example above, you can see that this B is the least element of your set X. Right? It's comparable to everything in capital B, and it is less than equal to that. But you see, in this case, it's not an analog of the upper bound in the sense that it is not a lower bound, because we are also making a restriction that B has to belong to this cap. It cannot be out of B, right? For example, if you take the same example, if you take the same example as before, W prime. Yeah, if you take say this set to be U, amazing. If you take this set to be U, let's give this a name. Let's call this point X. So if you take U to be this set, X, B, and W prime. Can you see that W is an upper bound of this?
W prime.
W,
Oh, W, yeah. W is upper bound.
right? W is an upper bound.
But we don't have that W and W dash are comparable.
Sorry?
If we don't have that W and W dash are comparable.
Right. Let's take out. Let's kick W prime out of the set.
Why are you taking?
Okay, let's push it out. Let's remove it from the set. Let's not be rude towards W prime.
It's like X, B, W prime. X and W prime are the maximum elements. There are two maximum elements, right? In X, B, W prime.
Yes, correct.
Yes.
Yes. X and W prime would both be maximal elements. Yeah, and if you take this set, just X comma B, then X is a maximal element, but W is not a maximal element because we require the maximal element to be a part of the set, to be an element of the set. Similarly, this element B is the least element of U. I consider this set. Let's say we have this one more relation, X less than equal to W prime. Now, if I take my B to be, say, just X comma W prime, then you can see that X is a least element of B, right? Can you see that?
Can you repeat what you just said? My net got disconnected.
Yeah. Take B to be the set X comma W prime, then X, little x, turns out to be the least element of capital B.
Least element of?
Capital B.
Yeah.
Yeah. But this small b is not a least element of capital B. Because least element is supposed to be a part of this, an element of this. But this B becomes a lower bound of the set. You see, just like we defined upper bound. There's also a thing called a lower bound, which is just the dual of that. But anyway, we won't be needing lower bounds. Anyway, so we have defined a least element. One more definition, too many definitions here. Let x comma less than equal be of partial order. Then we say that x comma less than equal to is a well-ordered or a well-ordered set if every non-empty subset of x has a least element. Can you think of a very easy example of a well-ordered set?
Just a line like a chain, one pointing to the next.
Yeah,
Just the
works.
set of integers, right? That also works.
Integers are not well ordered. You see,
Oh,
you take
can
all the integers, they don't have a least element, or
Oh,
just
right.
even integers or whatever.
Oh, basically, like any lower bounded set on real numbers would work. But
Again,
that also won't
no,
work. That also
no,
won't
no.
work. We can just
If
take.
you take a lower bounded set, yeah, take the open interval 0, 1. It does not have a
Yeah,
least
yeah, yeah. That I realized.
But you see, natural numbers work really well.
But
Because every
why
non-empty
doesn't
subset
the lower
will have a
bounded
least.
real sequence works?
Sorry?
Why doesn't the lower bounded real set work? Does not work.
Oh, I couldn't understand. What?
I'm saying why doesn't the lower bounded real set does not work?
Oh, take a look at the open interval 0, comma 1. Does this have a least element?
No.
Right? You take any element in this, I can find a smaller element than that in the same set.
But in a closed interval, we can get it.
Yes, very good. If the element is closed on the lower side, you don't need it to be closed on the upper side. It can be open or closed.
Yes, yes, yes.
This kind of stuff works. Nice, good. So this does not work. This works. Anyway, you always have singleton sets, with the trivial partial order on it. Star is less than equal to star. Then it's a well ordered because the only non-empty subset is the set itself, and it has a least. Anyway, so we have defined a well ordered set. That is good enough for now. Now I'm going to write 3 statements.
What's star?
And I want you guys to just any singleton set. Just couldn't think of.
Oh, singleton as in one element, right?
Yeah.
Oh.
Okay, cool. So far so good. Yeah, now what I'm planning to do is I'm going to write down 3 statements, and each one of them is saying something powerful in some sense. So yeah, first I'll write them down, then I'll talk. First is called the axiom of choice. Yeah, the statement goes as follows: let A alpha, alpha belonging to some set, be a collection of sets. In fact, a collection of non-empty sets. Such that lambda is not equal. Then lambda is not equal. Then there exists a function C, let's call it, from lambda to the union of all A alphas, such that C of alpha belongs to A alpha for every alpha. Right? So let's say you have a collection like this, a non-empty collection of non-empty sets, meaning all A alphas are non-empty. Then there exists a function from lambda to the union of all A alphas such that, C for choice, by the way. There exists a choice function from lambda to the union of all A alphas such that your choice at alpha belongs to A alpha. Basically, what this is just telling you is that you can choose an element from every alpha, every A alpha. Cool. I'll write down the second statement here. It's called Zorn's lemma. Oh, by the way, any doubts, feel free to stop me and ask. So
Can you give 1 minute to like digest this axiom of choice?
Yeah, cool.
like you define A of alpha such that alpha belongs to lambda. What does that mean?
A of alpha. Oh, that's just a family of sets, a collection of sets. Meaning your lambda could be some indexing set, say 1, 2, 3. Then A alpha, this set is just A1, A2, A3. Some sets. This collection
Oh,
is just
oh.
something like this.
All right.
Right? It's a collection of sets, and the sets are indexed by alphas, where alphas come from some collection lambda. Meaning for every element of lambda, there is a non-empty set A alpha.
How does this help? Like, I don't see any point of this memo.
You will see. Okay, here's the thing. So set theoretically. Okay, let's say you are working in real numbers. Okay.
Yeah.
Let's say this is R, your set of real numbers. This is a point 0. Can you guarantee that there exists? Let's not take 0. Let's say A is a real number. Okay, A belongs to R. This is A, and you only know R. You don't know elements of R. Let's say for now. Said theoretically, can you prove that there exists a sequence converging to A?
Converging.
Huh? Yeah.
Converging.
A sequence whose limit is A.
So like just take like A minus N, A minus N minus 1, so on. What do you mean by set theoretically?
Yeah, but see, you let's say you don't know about the addition and multiplication. You just know that R is a set with some distance on it. You only know how elements are placed.
Okay.
So, like it happens in metric spaces that sometimes in order to prove the existence of a sequence converging to a point, what you would do is you would take a look at A minus 1 by N, A plus 1 by N, like you said, but the set of all elements that are at a distance at most 1 by N from the point. So first you look at the set A1, which is the set of all points that are at a distance 1 from the set, from A. Then for A2, you have the distance. Take the set of all elements which are at a distance almost half. Yes. And you define this. And now because of axiom of choice, you know that you can pick one element from each of these sets. And that gives you a sequence converging to. Because
okay, even by axiom of choice, how about like, okay, we have this A1, A2, A3 sets as you defined. We can, okay, let's say for now, A is just 0 for ease.
Okay.
We can pick C of C1 as just, let's say, 0.5, C2 as minus 0.25, C3 as minus 0.2,
yeah,
plus 0.2, and then we can just alternate between plus minus plus minus. It's possible it doesn't, like that sequence is not converging, right?
It does converge.
It converges to 0.
It gets arbitrarily close to 0, right?
Like if a sequence converges, shouldn't it be like it should be only one side of the real number line?
Oh no, that's not the case. So okay, let's define a limit. Yeah, sidetrack, major sidetrack, but yeah, let's do it. Let AK be a sequence. Then we say that it converges to A, or A is a limit. Same thing. AK converges to A, or A is the limit of AK is given any say epsilon greater than 0. There exists a real number delta greater than 0. Oh, sorry. There exists a natural number n such that for every n greater than or equal to n, distance between A and an is less than epsilon. Does this make sense?
Yeah, so it can be both sides. Yes.
Right. What I'm saying is, given any positive epsilon, no matter how small, there will exist some n such that beyond that n, an plus 1, an plus 2, everything will be, at most epsilon close to a.
Yep.
That's what being a limit means. And it turns out, when you don't know what your elements of your set are, like in real numbers, you know what your elements are, real numbers. But let's say you have a set with some distance function d defined on it. You don't have any addition or something where you can't do that mumbo jumbo. A plus 1 by n, take the limit of all those. You can't do that. So you need the axiom of choice to be able to confidently say that there is a sequence that converges to it. If each of those balls around A is non-empty, then you can pick one in each of them and you can get a sequence. Cool enough so far?
Yep.
Okay. Yeah. So yeah, I think axiom of choice is done. Let's state Zorn's lemma.
So one
The
doubt
part
is set
Yeah.
theory so much of definitions.
Yes.
Sad.
It's not sad. See, the best thing about it is, when you do say algebra or something, you have a lot of tools because you have set theory already. In set theory, you are building those tools themselves. So it's a lot more primitive branch of mathematics when you compare it to other branches. So there are bound to be a lot of them. Anyway, now I won't be defining anything. I'm done with defining whatever I wanted to. Now I'm going for some interesting result. A damn interesting result. Anyway, but I'll make these three statements. Let x comma less than equal to be a partially ordered set. Be a coset such that every chain in X has an upper bound. Then,
What's a chain?
Totally ordered subset.
Subset.
Yeah.
Okay.
So a subset of X is called a chain if any two elements are comparable in that subset.
Okay. Oh yeah, you told it.
Yeah. If this happens, then X has a maximum limit. And this is a very strong statement to me, because what I'm saying here, or what Zorn is saying here, is that if you have a partially ordered set that every chain has an upper bound, then your coset will have a maximal limit. Like think of when a partially ordered set would not have a maximal limit. Suppose X is a partially ordered set that does not have a maximal element, which means given any element, you can always find another element which is strictly bigger than that, right? Because there are no maximal elements. Am I making sense here? Like suppose you have x comma less than equal to is a coset and it has no maximal element. Then given any element in this set, there will exist another element such that this element is strictly bigger than that. Right? Because x0 is not a maximal element. If no such x1 existed, then x0 would become a maximal element. So given any x0, you can find an x1. But now again, x1 is also not a maximal element. So, there should exist an x2, which is strictly greater than x1. And you can keep doing this. And you can build a sequence and see what you get. This sequence is nothing but a chain. Any two elements in this are comparable. And this cannot have an upper bound because you can always keep on adding new elements to the chain because there are no maximal elements. And Zorn's lemma is precisely telling you that this is the only thing that can go wrong. Having a chain without an upper bound is the only thing that can go wrong. That's the only thing that can stop you from not having a maximal element. Am I making sense or have I stopped making sense?
Yeah,
Have I
it makes sense.
successfully confused you all?
Yeah, kind of. Like I get that you are saying that for maximum element, if there is no maximum element, you will get a chain,
Yes.
but that will be an infinite chain, right?
Yes, it will be.
Yeah, okay, that's fine. Because if it's finite, then at some point it has to stop, and that will be the maximum element.
Correct. Makes sense. But Zorn's lemma is telling you that, that's the only thing that can go wrong, which is a very strong thing to say. That the only thing that will stop you from having a maximal element is a chain without an upper bound. Anyway, I'll come back to this later. And the last statement that I want to make here is called Zermelo's theorem, which says given any set x, any non-empty, any set x, empty is also. Given any set x, there exists a binary relation on x.
So how do we prove Zorn's lemma?
I'll come to that. Hold on.
Okay.
Just be a little more patient. I'm coming to that.
Okay.
Let's state Zermelo's theorem. Given any set x, there exists a binary relation on x, say less than equal to, such that x with this relation is a well-ordered set. Cool. It's just telling you that every set can be well-ordered. Yeah, which is again a very
What's the
strong statement.
definition of well order?
It's a partial order such that every non-empty subset has a least element.
Oh, okay.
Natural numbers was an example of that.
Oh, right. Yeah, good.
Is the proof just the construction? You can just like take it in a line.
No, that's the best thing. Take real numbers. Try to define a well order on that.
Okay.
Yeah, you'll see how difficult of a problem it is, because we as humans still don't know of a well ordering on R. We just know that it exists because of Zermelo's theorem, but we still don't have it explicitly.
Okay, so basically you don't have a proof of Zermelo's theorem. It's just Axiom.
No, we do have a proof of Zermelo's theorem. We just don't have a well ordering on R.
Like if you have the proof, just like replicate it on R, no?
But the proof is not constructive. It's existential. It tells you that there exists a well ordering. It does not give you a recipe to construct it.
That's sad.
It is sad. But see,
is there any prize if you find a well ordering on R? Oh, sorry.
I think so. I think proven. I think that you cannot explicitly write down a well ordering on R or something. Yeah, some sad stuff has happened over there in history.
Which contradicts Zermelo's theorem. If
No, it doesn't.
if you cannot write it explicitly, how does it exist?
I mean, why not?
Counterintuitive though.
It is counterintuitive. It's like the axiom of choice, right? It's telling you that there exists a choice function. You can choose one element from every A alpha, but it does not tell you how to choose.
Hmm.
right? Let's, like A alphas could be anything. They might not be sets that you know of. How do you choose something from an arbitrary collection of non-empty sets? You don't have a recipe to do that. But the axiom is telling you that a choice should exist. And you would like to have a choice there. Because choices are good. Same thing with Zorn's lemma. It doesn't tell you how to obtain that maximal element. But it tells you that it exists. All three of these are existential statements. And it turns out all three of them are equivalent. You can use any one of them to prove any other. So this is
If a
Yeah.
if a well-ordered set is like any subset contains a least element, is that what it is?
right. Any
But what if
non-empty
it's like
subset has
unbounded on the bottom or not infinite? Is that what you said?
So you see, it's telling you that given any set, there exists, like you can put an ordering on it, which is a well order.
So like are the reals well-ordered?
Not with the usual order, but there exists some other binary relation, which is an order, which turns out to be a well order.
Oh, so it's not ordered with the usual one. Okay.
Not with the usual order, right? You take the entire set of real numbers, it doesn't even have a least element.
Okay. Understand. Okay.
Not just subsets. R itself doesn't have a least. Yeah, but I mean, that's not the only order you can define on R, because order is just a binary relation satisfying some properties. It's just a set theoretic thing. I mean, given a line, you don't have to place the real numbers on it the way Euclid did. You can place it anywhere. I mean, that is if you're a set theorist. If you're into geometry, then you're kind of in a bad place. Anyway, so the big result. Axiom of choice. If and only if. Zorn's lemma. If and only if. Zermelo's theorem. So yeah, which proof would you like to see first?
Axiom of choice to zones.
Yeah, Zorn's with what? What implies what?
Oh, zones implies axiom of choice.
Zorn's implies?
Axiom of choice.
Okay. That proof goes through Zermelo's theorem. I'll do that.
So
So
we can do the other way then first.
axiom of choice implies Zorn's lemma.
Yes.
Going to do that.
Can you give a minute or so to think about it?
Yeah, sure. The thing is, I think we can finish one implication there. Oh, okay.
Like axiom of choice implies Zorn's lemma. Didn't we kind of go through the proof?
Yeah, that's the longest proof.
The longest one.
Yeah. So I'll tell you, the shortest one is Zermelo's theorem implies axiom of choice, which is a 2-line proof. Then there is the longest proof, which is axiom of choice implies Zorn's lemma. And there is a nice cute proof that is Zorn's lemma implies Zermelo's theorem.
Okay, can I try for Zermelo implies the axiom of choice?
Hmm?
Can I try for Zermelo implies axiom of choice?
Yeah, cool. So what I'll do is I'll give a 2-line proof of Zermelo's theorem implies axiom of choice. And then I'll do Zorn's lemma implies Zermelo's theorem.
Yeah, like can I say the proof?
Huh?
Like can I say the proof, what I think is the proof?
Yeah, sure. Give it a try.
The least element, we can just choose the least element in the subset for each of them.
Perfect. Nice. Who is this talking?
Siddharth.
Nice. Good job, Siddharth. So yeah, you have Zermelo's theorem, and this implies axiom of choice. Let's do that. So the proof is simple and clever, as given by Siddharth. Let A alpha, whatever, this be your collection. be a collection, a non-empty collection of non-empty sets. You know that by Zermelo's theorem, there exists a well ordering. There exists a well ordering. There exists a binary relation less than equal to on union of A alphas, such that union of A alphas is my X, such that this becomes a well order. This is a well order. And such that this is a well ordering. And now just give the function C of hold on. Just define the function C from lambda to union of A alphas as C alpha is the least element of A alpha. That does the job, right? Kills the problem right away. We wanted to show that there is a function from lambda to union A alpha such that for every alpha your choice lies in A alpha, and we know that every A alpha is non-empty. So by the well ordering principle or by the Zermelo's theorem, you know that every A alpha will have a least element. Just take your function to be that choice. Choice at alpha is the least element of A alpha. Yeah, perfect. And you have a function, and axiom of choice is proven using Zermelo's theorem. Thanks to Siddharth. Cool. What do you think? Let's have a quick attempt at Zorn's lemma implies Zermelo's theorem. What do you say? Oh, hello.
I don't understand how this proof works. Can you tell me?
Okay, good. Yeah, I'll go over it again. So axiom of choice tells you that given any collection of non-empty sets, call them A alpha, given any collection of non-empty sets, there exists a function C from your indexing set lambda to the union such that C of alpha for every alpha in lambda, C of alpha, meaning your choice, lies in A alpha, right?
Yes.
You can choose one element from every A alpha. Now, what we are doing is, you already have these A alpha. Just take the union. Suppose X is the union, right? X is the union of all A alphas. Now, by Zermelo's theorem, we know that there exists a binary relation on this, which is a well ordered.
Yes.
Zermelo's theorem says that every set can be well ordered, right?
Yes.
So pick a well ordering on that. Take a well ordering on that. And now, because it's a well ordering and every A alpha is a non-empty subset of this union, every A alpha will have a least element. So now you can just give the function. C alpha is the least element of A alpha. You're done. It's a function.
We can also put the max element of A alpha, right?
See, max elements need not exist because it's a well ordering.
Oh,
Take
so it can be infinite.
natural
right?
numbers. Yeah, take natural numbers again. Non-empty subsets will always have a least element, but they are not guaranteed to have, largest element.
Right. Okay, yeah, I see.
Yeah. Every non-empty subset having a least element and a greatest element, it's too big of a restriction to put on. Too big of a restriction to put on a set or on an order. Well ordering is nicely in the sweet spot where you can do good stuff with it. Anyway, so is this clear, or is there still something that I should explain?
Yeah, it's clear.
Oh, it's clear. Okay. So what do you say? Let's do Zorn's lemma implies Zermelo. This is a nice proof. I like this.
Yeah.
Oh. Yeah. So let's recall Zorn's lemma and Zermelo's theorem. Zermelo's theorem is easy. It just says every set can be well ordered. Every set has a binary relation on it, which is a well ordered one. Cool. Zorn's lemma, on the other hand, says that if you have a partially ordered set x comma less than, such that every chain in x has an upper bound, then x has a maximal element. So all you need is you want every chain to be bounded above. That is, you need every chain to have an upper bound, and that is enough to guarantee a maximal element. That's what Zorn's lemma is telling. So yeah, let's do this. Let x be a set. Oh, the proof. Let x be a set, and let f, this script f, be the set of all couples a comma less than equal to subscript a, such that a is a subset of x and a comma less than equal to a is a well ordered. I'll explain. Hold on. Okay, so what I'm defining here, this script f, is the set of all pairs a comma some relation less than equal to a, where a is any subset of x and this less than equal to is a well ordering on a. Fair enough? Like, are we comfortable with this set?
Also, aren't we playing Zorn's implies Zermelo, so we cannot like assume a well ordering, right?
Yeah, we can't assume a well ordering. We are not saying that every a will have a well ordering on it. We are just saying that f is the set of all subsets that have a well ordering on it.
Ah, all right.
Right? Yeah. So just take all those a's that have a well ordering on that have well orderings on it, along with those well orderings, and make a pair out of them and take the set of all those pairs and call that f. Cool so far?
Yes.
Oh, for example, if you take the empty set along with the empty relation, then this guy belongs to f. Because by definition, it's a well ordered relation. Every non-empty subset has a least element because there is no non-empty subset. Or you take any singleton subset of f, a subset with only one element, of x. Take a subset of x that has only one element and just give it the only well ordering it can have. Like the element is less than equal to its. That's a well ordering. You agree? Like for all a belonging to x, you have this thing, singleton set a with this relation. There's an element of this where a is related to itself in this relation. Fair enough? What I'm saying is, for on singletons, you can easily define a well order, right?
Yeah.
Yeah.
This is
So
like you don't even need a well order. Like just take the binary function as the number itself. Right?
yeah, I mean it's just a point with a loop. That's always a well order. Okay, are we comfortable with this F? Questions?
Yeah.
Have I been successful in confusing you all so far?
Kind of a bit.
Yeah, so my aim is to show that X has a well ordering on it, right? Because that's what I'm going for. I'm proving Zermelo's theorem. And I'm going to use Zorn's lemma on the way, along the way. So I'm starting by saying that let X be a set. And now this F, this guy, I'm defining as the set of all pairs, all possible pairs A comma less than equal to A, such that A is a subset of X and A with this binary relation is a well ordered. That's all I'm saying. Cool. Should I go ahead or should I explain something?
Yeah, it's fine, I think.
Okay, fine. So yeah, we have this F. Now I'm going to give a partial order on F. Okay. I'm define a partial order. Let's call it your symbol on F as follows. Two elements of F. We say they are related by this relation. If and only if the following. First, we need A to be a subset of B. Second, we want this relation to induce less than or equal to A on A. I'll explain what this means. And thirdly, for all B belonging to capital B minus A and A belonging to A, we must have A less than equal to B.
What does
Why I
point
put
two
that?
mean?
Huh?
What does point two mean?
Yeah, I'll explain. So you have okay. So for what it means for less than equal to B to induce less than equal to A on A is that whenever for all A1 comma A2 belonging to A, we have A1 less than equal to A2 in A, if and only if we have A1 less than equal to A2 in B. Right? So what that means is you have the set B, right? It's some partially ordered set. I don't know what it means. I don't know, something. Some partially ordered set. Let's say this is B. And suppose A is a yeah, A is a subset of this. Let's say this, this, and this. Then the order less than the order induced by this less than equal to B on A is just all these lines that involve the points of A. I like how nicely I'm drawing all of this.
Looks like a butterfly with something. At least the green part.
Oh, yeah, so it does. Yeah, so does that make it clear what I mean by inducing less than equal to A?
I get what the 3 points mean.
Yeah, so yeah, I'll just
I don't
elaborate
get
on
what
the
the diagram means.
yeah, what I'm saying is if B is this diagram, B comma less than equal to B is this diagram, and A is the set of all these green points and this black point that I forgot to say. If A is the set of all circled points, then the order induced by this bigger diagram on A is the green diagram.
What is order induced mean?
Yeah, just defining something. We see that this green diagram is the diagram induced by this bigger diagram on this set. Right? Which means that in green color this will hold if and only if it holds in the black color.
Right.
That's what we are seeing. Right? Like yeah. So you have B with its order on it less than equal to B. That's the order. And you look only at the points A, then you look at what the order looks like only on those points. And that's the order induced on A. What I'm saying is that should precisely be this order that we started. So if these three conditions hold, we say that this pair is less than this pair. Cool? Yeah.
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 Also, so like basically, if we get any other element in B, not in A, then
Yeah.
that should be greater than an element of A, right?
Yes, exactly.
Okay.
So elements that are in B but not in A are greater than every element of A. So if you have an element in A and an element in B which is not in A, then the element which is in B but not in A will be greater than that element in A. Right? Meaning every point that is black but not green will be greater than every green point, which makes me think I should draw an arrow here. Better. Cool. Every point that is black but not green is above every green point. Basically, what this means is, A is a well ordered. Let's say it's a set of points. It's a well ordered like this, and every non-empty subset has a least element, and B is also something. What this is telling you is that A is an initial segment of B. Like everything that is in B but not in A will be strictly greater than everything in A. And the order on B, if you reduce it to the set A, you get the same order on B. So what this is telling you is that A is an initial segment in some sense of B. but it's usually better not to picture them as linear sets. I mean, sometimes it is, but better keep it up. Anyway, so now we have this new order on this set F, right? You have given F this order, and you can check that this is actually a partial order because every pair A comma less than equal to A will be less than itself because A is a subset of A. You know, less than equal to A induces less than equal to A on A, and there is nothing which is in A but not in A. Yeah, so life is easy, and you can check for transitivity as well. Things work out nicely, and so check this F with this fancy less than is partial order. Cool. So now we are free to use Zorn's lemma. All we have to show is that every chain in F will have an upper bound. If we can do that, then F will have a maximal element. So let's do that. Let A alpha comma less than equal to alpha be a chain. Let's let's not index too much. Let this be a chain in F. Okay. Remember, by chain what we mean is this is a subset of F which is totally ordered. So now given any two elements of this set, A alpha less than equal to alpha, A beta less than equal to beta, you can compare them. Any two are comparable. So you will either have A alpha less than equal to alpha is less than this, or you will have the other. I don't know which. But it's a chain, which means given any two, they are comparable. Let this be a chain. Can you think of an obvious upper bound on this?
Oh, you can form a chain.
Hmm?
Oh, Zorn's exist. Yes.
Yeah, Zorn exists, but you can only use Zorn's lemma if your in your poset every chain has an upper bound, right? If you can show that, then you can say that your poset has a maximal element. Yeah. So let this be a chain. Take a look at this. Let A be the union of all A alphas. And I'm going to define a relation on it. For any two elements A and B belonging to first of all, they belong to A, and A is this union. So there exists elements alpha and beta such that A belongs to some A alpha and B belongs to some B beta. So and because it's a chain, one of A alpha and A beta will be less than the other. So say let's say A alpha is the smaller one. This makes sense, right? They will be comparable because we started with a chain. So one of them will be contained in the other. So that tells you, therefore, A and B both belong to A beta. And because A beta itself is a chain, you know that A and B will be comparable. So yeah, in beta. So this or this will hold. One of these two will hold. And whichever one holds, you pick that and you declare that as the order on A and B. So if A less than equal to beta, A less than equal to B in beta, then you write A less than equal to A and if b less than equal to a in beta, then you say b less than equal to a in a. Cool. So what I'm doing is I have this chain. So I have these elements. Let's say this is a alpha. It's a well ordered. Then I have a beta. Let's say this is a alpha. Let's say this is a beta, bigger than a alpha. Let's say I have some more elements. This whole thing is a gamma. I don't know. And this is a chain. What I'm doing is I'm taking the union of all of them. I'm taking the union of all of these a alphas, and I'm calling that union A. And whatever order, just pick any two elements over here. Okay? They will have some ordering over here, which is coming from the smaller sets, from the A alphas. Because it's a chain, there will be some A gamma containing both of them. And you look at the order over there and you declare that as the order on A. So, you know, A gets an order such that the order induced by that order on any A alpha will be this less than equal to alpha. So the second condition is naturally satisfied. But yeah, let's take a look at all conditions separately. So clearly, one A alpha is less than equal to A for every alpha, because A is the union of all A alpha. Secondly, this new order that we have defined, it induces less than equal to alpha on A alpha for every alpha. And thirdly, let's say uh, let's say B belongs to A, but not to A alpha, and A belongs to A alpha. Then you see that B must belong to some A beta because it belongs to A. You notice A is the union of all A alphas, and B belongs to that union. So B must belong to some A beta. But note that B does not belong to A alpha. So B must belong to this set. And this tells us that A alpha comma less than equal to alpha must be less than A beta comma less than equal to beta. Oh boy, bad handed. Anyway, yeah, it must be like this. And now you have B belonging to A beta but not to A alpha. You know, this tells you that B is less than equal to in A beta. But then that tells you that A is less than equal to B in A. And that does the job. We have checked all three conditions. So this tells you that this gives A alpha comma less than equal to alpha is less than this new set that we have built for all alpha. Right? Also, exercise. Check that this thing that we have built, A comma less than equal to is a well ordered. Why will it be a well ordering? Let Q be any non-empty subset of A. Then for for some alpha, you will have Q intersection A alpha to be non-empty, right? All of them cannot be empty because Q itself is non-empty. So some intersection will be non-empty. And then you also see that Q intersection A alpha is a subset of A. Therefore, so this is the part that you have to check as an exercise. The least element of Q intersection A alpha is also the least element of Q. Least element of Q. Cool. So what have we just shown? We have shown that for every chain, we started with a chain and we constructed a well ordering, A comma a well ordering, this thing, which is an upper bound for the chain. So this tells us that every chain in F comma less than has an upper bound. Every chain over here has an upper bound. And what does that tell us? We are free to use Zorn's lemma now. What do we get? If this is a partially ordered set,
It
in
has
which
a
every
maximum
chain
element.
perfect. Therefore, by Zorn's lemma, this thing has a maximal element. What should we call it? Call it E comma less than equal to. Okay, this is a maximal element of this guy, F comma bigly less than. But now I make a claim. If E comma less than equal to E is a maximal element of this, then E must be equal to X. Can you see why?
What was X?
Oh, X is the set that we started with.
So like it's
Yeah.
the maximum element, so everything should be in it. So it means it should be X only.
No. It's not the maximum element. It's the maximal element. It just
E.
tells you that there is nothing greater than that.
Oh.
Yeah.
Yeah, so like the way we defined our post set,
Hmm.
every other set is a subset of that E.
Oh, need not be. That's the thing.
Oh, right. Like, see,
Yeah,
there are
it's
three
all
sets.
these three conditions. It's not just the first condition. Right. What if you have the
Oh.
same set E with some other well ordering on it?
Oh,
A set
okay.
can have two
I
different
got
well orderings.
Yeah, so like see, E is the maximum element. So it means that also it's a chain, right? We have a chain because we use zones.
Okay.
So let's say we have like U, V, W. Oh, okay, no. What was the set E, right? We have, let's say, C, D, E. And then C is in the order C, then comes D, and then comes E in the chain.
Okay.
So C is a subset of D, right?
Yes.
And D is a subset of E. So eventually C is also a subset of E. And thus every set is a subset of E, no?
But that is only if you have C less than D less than E.
Yeah, that will be holding because like it's a chain, so every set should be there in chain somewhere.
Okay. Here's a question. You know that you can reverse orders, right? Oh, wait. Let's say E has two different well orders. Let's say E with this relation and E with what is it? let's write it, are both well ordered. Then you can't compare them, right? Let's say these two are different different orders. Then you can't put this or this between them. You can't really compare them because look at condition 2. For them to be compared like that, you need this. Oh, why am I writing with an eraser? So dumb. Yeah, you need this condition. You need one order to induce the other order, which is not happening. It's not that difficult. See, suppose E is not X. Suppose E is not equal to X. It's only a proper subset of X. Then there exists an element E belonging to X, but not to E. Right? So now you have this capital E, which is a well ordering, as we are saying, whatever the relations are. I'm bad at trying. This is your E. What I can do is I can just put this E on top of everything. Okay? I can just put this element E on top of it, on top of everything. And this is still a well order. Right? If I have a well ordering and I adjoin an element on top of everything, then E union this E with this new order, which is the same thing but with an additional E on top, is also a well order. But this is a contradiction, right? Because this element is strictly greater than E, strictly greater than this, whereas this is supposed to be a maximal element.
How is this a well order? Can you tell me?
So, did you understand what this order is? Any two elements, if they are in E, we keep the same order, and if one of the elements is E, it's greater than the other. Fair enough? You had this. Okay. So you have this E to begin with, whatever the lines are. Yeah. Drawing. So you have this E to begin with. Any two elements, A and B, let's say A less than whatever. You have this, things like this. And you have this element E, which belongs to X but not to E.
Yes.
Now what I can do is, I can just take this E and I can declare it to be greater than every other element, every element in E. Just declaring it to be greater than every other element, every element of it. See what I'm doing?
Yeah, then E is the maximum. Yes.
Is the largest element, but now you see this bigger set that we have formed is also a well ordered. You take any non-empty subset of that will also have a least element because
yes,
E is a well ordered.
But what if, like, let's say E is less than something? It can be possible, right?
Yeah, but I'm declaring the new order like that, right? I get to define this order. Yeah.
I see.
I'm declaring this E to be greater than everything in capital E. But now you see I've obtained a well order which is bigger than this, which should not happen because we said this was a maximal element. We shook hands on this, remember? Have I
Yeah.
confused you all?
I got the main idea. Yeah, like I will have to check details, but I got the main idea how it's.
You understood. That's sad. My aim was to confuse you.
Okay. Like I don't remember. Like if you ask me to like rephrase the proof, I won't be able to. But like
Yeah.
more, you can say like in the first 5 minutes, maybe.
No, it is too much to take in.
Also, you'll be sharing the notes, right?
Yes.
Oh, okay, then nice.
It's loaded with a lot of information. You see, that's the best thing about set theory, that you get to make really strong statements with really minimalistic notation and definitions, because you don't have big tools like you do in algebra, analysis, calculus, whatever.
Yeah, everything is just from like very basics.
Yeah, we
Like,
start
what we
from
use
scratch.
every day is like we're proving now.
Yeah.
It's like we are just trying to think of logic and stuff in
Sorry?
the most basic. Like it's like we are trying to think of logic and stuff in the most basic and purest form.
Yes.
It's like you write a triangle and then say prove it's a triangle.
Oh, there was like a 600 long page proof of that 1 plus 2 is equal to 3 or 1 plus 1 is equal to 2.
Oh God, how
I-
aren't the numbers defined that way? Like 1 plus 2
No,
is 3.
like that guy defined the operation, then thinks it was Butler and Bressel, I guess. He just defined the, it was in Principia Mathematica. It was like a 600 page proof. And it just used like a tons of logic and stuff.
Wow.
I guess I'm personally a bit interested in these stuff.
Oh, by the way, how much time do we have left?
5-10 minutes? Or do you need to
Oh,
cover
okay.
more?
No, like I can stop whenever you want me to stop. I can keep going on for set theory. I can keep talking whole night.
Yeah, I understood
I
your
don't
look.
want to fry your brains though. I don't want
Ah.
to do that.
I think we can just stop now because like the time was till 8:30 and
Cool.
you have like differential equation class at 9.
Cool.
Also for the different, I'll stop recording.